Alright, this is going to be my workshop on PIDs, how to tune them, what they're used for, and all the good stuff like that. I didn't make this slideshow, but it's something made for a first team that I found was pretty good. And this is understanding PID control. So, first of all, what is like an actual controller, and why would you want to use a PID? Basically, for robotics, we use a PID in everything from making the robot drive, making the flywheel spin up to a certain speed, making an arm go to the angle we want to. It's how we tell the robot, hey, we want to go to a specific angle, and the robot does it. And it takes in a couple of parameters. It takes in your process variable or output. This is what you're trying to control. So let's say your arm angle. If you say set your arm angle to 30 degrees, you're trying to change your output variable to that specific angle. There is the set point, which is what you're trying to set it to. So let's say you want that arm to go to 30 degrees. Your set point is 30. There's the control output. That is generally going to be your motor power. So you're trying to get your output variable to your set point. You're changing the control output. The thing you feed into the controller is your error. That's how far off your output is from your set point. So let's say you're currently at 20 and you're trying to go to 30, your error is going to be 10. And the last thing is your gain. I call these your PID constants. There's a bunch of different names for them. They're denoted by a K. So you see KP, KI, KD. That's your gain for each of your different PID constants. So when you're tuning a PID controller, you want it to be something like this, where you very easily just taper off at whatever your set point is. This horizontal line is going to be your set point. And oftentimes it's not as good as that, but that's what the goal is in any of these controllers. The basics are open loop controllers. We try to avoid these because they're, by design, they're inaccurate. They don't adjust for anything. They just set a power based on whatever you want to do. I'm going to brush over that really quick because that's not very important for this. Same thing with bang bang controllers. This is basically, if you're over the target, set a certain amount of power going down. If you're under the target, set a certain amount of power going up. These are inaccurate, and they work for some simple scenarios, but they cause oscillations like this. And you'll see this partially with PID as well, but with PID, you're able to tune the PID to avoid those oscillations, and it'll be a lot cleaner. So, in the basics of PID, this is your equation. This is a bunch of math. You don't really have to know this. There is a bunch of code libraries that'll handle this for you, whether you're coding in Java, C++, anything. Yeah, come in, it's fine. No matter what language you're coding in, you're probably going to find a PID library for it. It's not a big issue. You don't really have to know this, but understanding the basics is good. So you see your KP, basically ET is your error, and then you have your constants. The KP, that is your proportional. So you're taking a value and multiplying it by the error. Let's say you're 3 degrees off, and your KP is 2, you're going to be powering the motor with a factor of 6. Your integral, that adds up all the error over time. So the longer that you go away from a target, the stronger your I value is going to be, the more power it's going to be applying to the motor. And KD is called your derivative. I've also seen it called the damper. What it does is, if you're approaching the target too fast, it's going to throw on the brakes, figuratively, to prevent you from overshooting your target. And also, another thing I want to touch on is feed forward. That is basically, you sometimes use it, sometimes don't. It depends on your application. But let's say for a flywheel, you already know that you have to apply a certain amount of constant power depending on what your set point is going to be. So let's say you're at 4,000 RPM. You know you need to apply a certain amount of power. So that's where your feed forward terms comes in. Basically, when you set your set point to, let's say, 4,000 RPM, you multiply that by your feed forward factor, and that's going to apply a certain amount of motor power just off rip without the PID doing anything, and it makes it easier for the PID to react, and it's going to be more accurate as a result. You use feed forward in a couple things from elevators, arms, and flywheels, but there's some things where you don't need it, and I'll go over that later. First of all, as I said, the proportional. The proportional is the simplest term here. It's basically multiply your error by a constant and give it back to the motor so it goes the opposite direction. You're 3 degrees off, you multiply it by 2, your motor is going to try to power with a factor of 6 the other direction to fight that error. Let's see. in a P controller, there are simple things called P loops, and they work in some applications and they don't in others. The reason for that is this next slide here. They never really actually hit the desired target, and sometimes that's okay, sometimes it's not. But because there's always going to be a little bit of loss in the equation, like friction, as you get closer to the target, your response is going to get weaker with a P loop. If you're a single degree off, your P controller is only going to be powering it by like 3% of the motor power, and sometimes that isn't enough to counteract friction. So you're going to see something like this, where you get close, and then you taper off just short of what you wanted to hit. And sometimes that's okay, sometimes it's not. And when you're deciding what controller you want to do, you can choose any of these. You can set, in a PID loop, you can set some of the factors to 0. So for example, you could do just a P loop where it's P is equal to a certain amount, I and D are equal to 0. And it won't really respond to the rest. The next thing is integral. And the integral was to solve basically what the main issue with just the P loop is. Let's say you get pretty close to the error. The longer you go with a small error, the bigger the integral gets, the more power it's going to be applying to the motor. It's a little bit hard to explain, but what it does is, as it gets close, instead of stopping here, the integral gives you a little bit extra power so that you can hit this area and you actually end up on target. And it solves one of the biggest issues with P loops. So that's how you see PI loops, although they're not commonly used because they have another issue, oscillations. And when your error is big, your integral gets pretty high, and you see something called integral windup, which it's a little bit complex, but the farther away from the target you are, the faster your I value is going to get larger. And if you sit for a while outside or a long ways away from your set point, that I value is going to get very large and it's going to be hard for it to counteract. There's a couple ways of, there we are. There's a couple ways of counteracting it. Sometimes you can wait to have the I value kick in once you're close to the target, so otherwise it doesn't wind up. You can cap the value. There's a couple things you can do, although the FRC libraries normally have ways to handle that for you. Derivative is basically, the faster you're approaching the target, the more it's going to throw on the brakes. So if you're approaching the target really fast to the point where it's going to overshoot, the derivative is going to give you a little bit of negative power, and it's going to slow down the system a bit so it kind of glides to whatever your set point is. And that's what you're going to see here. With just the PI loop, you see how you very much overshoot. But with a derivative term, as you get closer to that set point and the faster you're moving, the more it's going to dampen out. And you're going to see a lot less oscillation. And a little bit of oscillation in a system like this is fine. But it's not, you don't want a very big oscillation because, I mean, have you guys seen systems where the arm will go bouncing back and forth until it finally hits the target? This is a bunch of math behind how PID works. I would say kind of ignore it. But the next thing is feed forward. I touched on it a little bit already. Basically, as you are trying to hit a specific target that requires consistent power, let's say our flywheel, you need a certain amount of power to just keep it going. And if you're using a regular PID, as you get close with a regular PID to your set point, the power is going to diminish. And for a flywheel, when you need a specific amount of constant power, that's going to be counteractive. That's what the feed forward term is. It allows you to give a constant amount of power to, for lack of a better word, just stay at that target. So as soon as you say set your flywheel to 4,000 RPM, the feed forward gives you a certain amount of base power, and then the PID acts like normal to get any excess error. The thing is, the feed forward has to be somewhat accurate, because if your feed forward isn't accurate, your PID is fighting a lot of error that's just caused by default by the feed forward term. And there's a couple ways to go about figuring out the constants for that. There's something called sysID, which I don't fully understand. Mr. Keith understands it. If you have more questions about it, ask him, because it's slightly out of my pay grade. But it's, you have basically a bunch of code that will give you some constants for your feed forward, and it allows your turret to, or your flywheel, to hit those, to hit the proper RPMs without much error generated by the feed forward term. Let's see, yeah. So for more uses of feed forward, basically the first one was controlling the speed of a motor. As you speed up more, you need more power. But with a PID, the higher, as you get closer to the set point, the PID automatically decreases your power. So you need more output, and that's how feed forward works in that. Another thing with an arm, as you get more to the horizontal with an arm, gravity is going to give you more force basically acting down on that arm. So using cosine and tangent trig, you can basically just, as you get further up with the arm, the motor will apply more power. As you get more vertical, the motor will apply less base power on top of what the PID's already commanding. Putting them all together, you get PID F, but normally we just use PID. Feed forward does come in specific scenarios. So this is a bunch of code that I'm not a very good coder, so I'm going to skip past. But here's the part that the class was actually about, tuning the PIDs. So for a PID to work, you need to choose the constants well, and you have options where you basically put in numbers for your P value, your I value, your D value, and in some cases, your feed forward value. But the PID only works well if those are chosen well. So the way that you manually tune it, which is how we normally do it in this team, first of all, you increase Kp, so your proportional value, until it oscillates a little bit like this. And that's kind of, if you put your Kp value too low, your system isn't going to respond fast enough. It's not going to be snappy, which is something that we kind of want. But if it's too high, it's going to oscillate like this. So you increase Kp just gradually until you see a little bit of an oscillation. And then you can put Kd into the equation. Kd will, how do I say this? So Kd will take you from that oscillating graph there to a much more damped one if it's chosen correctly. And you slowly increase Kd until you get the correct amount of dampening. If you over dampen the PID, it's going to cause some problems. It's hard to describe, but if you make Kd too high, the PID just starts spazzing out, and it's slightly obvious once you've gotten too high. If it's too low, you're going to see still the oscillations are going to be there. And you can keep doing that. Let's say you get through this and you get a nice curve, you want it to be snappier. You can increase Kp again, and then you can increase Kd again. But if you overdo it, it's going to start oscillating, so always be ready to revert back to where you were. As long as it hits this, your biggest goal with a PID is to get this nice curve without oscillations. And yeah, that's what it says in step 3, just keep doing it until it's snappy enough for you. And then the next part is if it's not exactly hitting the target, sometimes you'll see a response where instead of going here, this being your set point, it's going to stop a little bit short. And for some systems that's okay, some it's not. That's where you would add Ki. And if you add your integral, it's going to add a little bit of error, it's going to add a little bit of oscillation, but the thing is, it's going to make sure that you 100% hit that target. And you add a little bit, Ki is generally the smallest of the 3. It goes into a little bit later, the magnitudes here. Generally, every PID will come up pretty similar. So I'm going to ignore this one because that's a very broad statement, but generally, you're going to have your Kp value, and let's say your Kp value is 2. This is all speculation. It's not always like this, but then your D value is going to be about 1/10 of what your Kp value is. So Kp is 2, Kd is going to be 0.2. And then from there, Ki is going to be about 1/10 of what the Kd value is. So Kp2, Kp2, Kd 0.2, Ki 0.02. Something like that. And as it says here, all the K values are almost always positive. I've never seen one that was negative in my life. And yeah, that's generally how you do it. That being said, as you adjust it, you change some things. If you increase or decrease Kp too much, it's going to change the response time. If you increase it too much, it's going to oscillate before hitting the target. If you decrease it, it's going to be slow to react. And that's one of the issues, we can see that on our turret. If we decrease it too much, it just kind of turns slowly. If you increase it too much, the turret snaps but overshoots, and then wavers there a little bit before actually hitting the target. If you increase KI or decrease it too much, the same thing, especially because KI can create a ton of oscillations. And then increasing KD will dampen your oscillations, but if you increase it too much, it'll spaz out, and sometimes, or a lot of the times, it'll decrease your response time because it's slowing down whatever you're moving. It slows it down before it hits the target. But if you're needing to sacrifice a tiny bit of speed for more accuracy, that's okay. All right. I think we're good.